can be produced. With the help of magnetic field, current can be produced. So we will see how with the help of magnetic field the current can be produced or induced. Okay. So for the study of the induced current and all that, we should know what is the magnetic flux. Okay, so this chapter started from the concept of the magnetic flux. So like the electric flux we have studied, in the electric flux, what is the electric flux? Electric flux is the number of electric field line passing through an area perpendicularly. Number of electric field line passing through an area perpendicularly. Electric field line. What is magnetic flux? Magnetic flux is number of magnetic field line. Number of magnetic field line passing through an area perpendicularly. Suppose this is the area. This is some plane area, and this is some plane area, and these are the magnetic field lines. These are the magnetic field lines, and these magnetic field lines are crossing or passing this area perpendicularly. Okay, so suppose here these are the four magnetic field lines. These four magnetic field lines passing this area perpendicularly. So magnetic flux will be 4. Magnetic flux will be 4. The unit of the magnetic flux we will discuss later. Okay, and this magnetic flux is represented by this phi suffix v. So this is the area. Suppose these are the two magnetic field lines passing this area perpendicularly. So what will be the value of the magnetic flux? 2 magnetic field line. Okay,
2.
Yeah, 2. So for the study of the magnetic flux, we should know what is the area vector, not area vector. Okay, area vector. Like in the electrostatic, we have, I think some teacher had told you what is area vector. So here I am again discussing what is area vector. So area vector means the area and vector. Means if you will give direction to the area, what is vector? Vector is having the magnitude and direction, and follow the vector law. Follow the vector law. So basically, if you will give the direction to the area, that area will become the area vector. But how we will give the direction to the area? Suppose this is some area. This is some area. This is the plane area we have. And what will be the direction of this area? This is the point. What is the direction? So always remember, for the plane area, the direction of the area will be perpendicular to this plane. Perpendicular to this planar area. This perpendicular can be like this, and this perpendicular can be like this also. Like this also. Okay. So direction of the area will be perpendicular to the plane of area. Okay. So area vector can be written as area and the direction. Okay.
Yes, sir.
So suppose this is your area. A length into breadth is the area of this rectangle, and direction of the area. This is the direction of the area.
Yes, sir.
And direction of the area is perpendicular to the plane of the area. So this area is perpendicular to this vector. And what is this A cap representing? A cap is representing the unit area vector. Unit area vector. What is unit area vector? How you will calculate this unit area vector? Unit area vector can be calculated by area vector divided by magnitude of area vector.
Yes,
area vector. Okay. So we should know how we will convert area into area vector. So this unit area vector representing the direction of the area vector. Okay, right. Telling the direction of the area vector. So if you want to write what is area vector, not area. So first you will write area, that is length into breadth, and you will multiply this with the unit vector. With the unit vector perpendicular to the area, and this area vector, this unit area vector is perpendicular to area. Okay, perpendicular. Direction of area vector is outward normal. Simple.
Yes, sir.
Okay, now what is magnetic flux? This is very simple thing. Magnetic flux is given by so this is your area. Suppose ABCD is your area.
Yes, sir.
Okay. Suppose ABCD is your area. And this is the unit area vector, means unit area vector. And this
Yes.
unit area vector will be perpendicular to area. This we know. Suppose this is the magnetic field and this magnetic field is making an angle theta with the area vector. Then magnetic flux is given by V vector dot A vector. V vector dot A vector, and this
E
can be
vector.
open. This will become VA cos theta. VA cos theta, and like electric flux we have, this is the electric flux E dot A, like
Yes,
magnetic flux
sir.
is B dot A. So what is this? This is
Electric
the
flux E dot A.
yeah. This is electric flux. So what is theta? Theta is the angle between B and A, and this is the scalar product of magnetic field and area. So this uh, magnetic flux is a scalar quantity. Talking about the unit of the magnetic flux, this will be unit of magnetic field multiply the unit of area. So Tesla meter square, and this is also known as Weber. SI unit is Tesla meter square, also known as Weber, and CGS unit is Gauss centimeter square, and this Gauss
Maxwell.
centimeter square is no equal to Maxwell also, and 1 Weber is equal to 10 to the power 8
10 raised to
Maxwell.
8 Maxwell.
So this is
Yes.
the basic thing of about this chapter. This is the
Yes, sir.
basic thing about this chapter. So you can now write down.
So just hold on. Second scroll down. Second scroll down.
Yeah. So this is remember this theta. This theta is the angle between the area vector and the magnetic field vector. Okay.
Yes, sir.
Area vector and the magnetic field vector.
Sir, done, sir.
Okay. Instead of this a cap, na, the direction of a cap is representing the direction of area vector actually, na. So you can write here a cap also, a vector also. So okay, so change here, write here a vector.
Yes, sir. Yes, sir.
So now this is the, you should know this formula. Okay, you should know both these formulas. These formulas. These are important formulas. These formulas are important. Okay. Now we will discuss Gauss law in magnetism. There was Gauss law in electrostatics. What is the Gauss law in electrostatics?
The total magnetic flux enclosed in a surface is equal to the is 1 by epsilon times the total charge enclosed in the surface, right?
Okay. So before that, we will discuss how we will calculate the flux when the surface is curved. When the surface is curved. Okay. So suppose I am taking one circle here. No, not a circle. This is a sphere. This is a sphere. And in this sphere, suppose this is the magnet, north pole and south pole. What will happen? Magnetic field line from this magnet will be like this. Okay. North to south, north to south. So you can see magnetic field line are means starting from the north and existing at south. Means magnetic field lines are making the closed loop. Okay, because monopole does not exist. North and south always be there. Okay, in a magnet. So here the magnetic field line are making the closed loop. So what is the flux Here you can say entering flux is equal to the leaving flux.
Yes, sir.
Or you can say leaving flux. What is the leaving flux? This one line and this another line is the leaving flux. Entering flux is two line. This line and this line is the entering flux. So leaving flux is equal to the entering flux. So you can say here leaving flux is equal to entering flux. So what will be the total flux through the sphere?
0.
0. So net flux through sphere will be 0. Net flux is equal to 0. So if you are taking if you are taking entering flux as positive, then you will write here, suppose entering flux is phi 1 and leaving flux is phi 2. So what you will write, entering flux phi 1 minus phi 2, and you know that phi 1 is equal to phi 2.
Yes,
So
sir.
answer will be 0. So this is the Gauss law in magnetism. So you can say from the Gauss law in magnetism, the total magnetic flux through a closed surface is equal to 0. So this is the, and how you will calculate the magnetic flux through a closed surface? This is given by the B dot dA. Okay, B dot dA is the total or net magnetic flux is given by B dot dA, that is equal to 0.
0.
Yeah. This is the surface integral of
Yes,
magnetic
sir.
field. Like in electrostatics, uh, surface integral of electric field no, for calculating the electric
Yes,
flux.
sir.
So here the
Yes, sir.
surface integration of magnetic field. We have also studied the line integral. Where we have studied the line integral? Ampere's law, Ampere circuital law. Line integral of magnetic field is equal to mu naught I. So basically, from this surface integration or from the Gauss law in magnetism, there are very few question in there is, I think, no question in NCRT. Okay, so we should know what is Gauss law in magnetism. Okay, this you should write in Gauss law in magnetism. This is a part of Gauss law in magnetism, and this topic for the closed path, for the closed surface, the magnetic flux will be V dot dA. This is equal to phi b, and from here this is the Gauss law in magnetism. So Gauss law in magnetism says that magnetic flux through a closed surface is equal to 0. Just a minute, have you written this thing?
No, sir.
Okay, first write this.
Done, sir.
So Gauss law is magnetism now clear?
Yes, sir.
Basically, you will not get much question from this topic, Gauss law and magnetism, but you should know the statement. For a closed surface, the magnetic flux will always be zero because leaving flux will be equal to the entering flux. Suppose this is the closed surface and your magnet is here. Then what will happen? Again, the magnetic field line will be like this.
Yes, sir.
So you can see here, this is the entering line, this is the leaving line. So you can say the entering flux will always be the equal to the leaving flux. Okay. So okay, this is fine. Now we will discuss the numerical and this is the question. First question. Okay, I am solving this question. You should solve this question. First, I am solving this question. So in this question, magnetic field is given in the vector form. They are saying magnetic field of itna, magnetic field of this 10I 3J K Tesla exists in space of area 2 meter square in YZ plane. Calculate the magnetic flux. Calculate the magnetic flux. So So this area of 2 meter square is in YZ plane. Area of 2 meter square is in YZ plane. So this is suppose x axis, this is y axis, this is z axis. So area is given in the YZ plane. So this area is given. So this is the area. And what is the value of area? 2 meter square. Okay. Can I write the area vector of this area? Area vector will be area into unit vector in the direction of area vector. Okay.
Yes, sir.
So this area is in YZ plane. What is the unit vector perpendicular to this YZ plane? See, unit vector along x-axis is I cap, unit vector along y-axis is j cap, unit vector along z-axis is k cap. So see, this area is in YZ plane. This area is in YZ plane and I want to write the area vector. So for the area vector, I will write A into A cap. A cap means unit vector along the direction of area. So direction of area is perpendicular to this YZ plane. So this x-axis is perpendicular to this YZ plane. So what is the unit vector along x-axis? I cap na?
Yes, sir.
So first put the value of area 2 and write here I cap. Harsh, got it or not? Means are you
Yes, sir.
getting
Yes,
or
sir.
not?
Yes, sir.
It's very simple. This is very simple. This is your YZ plane. Area is in the YZ plane. We know
Yeah.
that unit vector or the direction of this area vector will be perpendicular to the YZ plane.
Yes, sir.
And perpendicular to YZ plane, which is the unit vector perpendicular to the YZ. This is the YZ plane. Perpendicular to YZ plane is x-axis. So what is the unit vector for x-axis? I cap, and that I cap we will multiply here. So area vector is 2 I cap. Now can we calculate the magnetic flux? So magnetic flux is given by B dot A. B dot A. So B dot A. So value of B is given 10I plus 3J plus K. 10I cap plus 3J cap plus K cap. Dot area vector 2I cap. This is in meter square. So can you solve this dot product?
Yes, sir. Yeah.
Okay, solve this. If you have any doubt, then you can ask me. Means this from this area vector and how I am taking the direction of area vector.
Sir, I think I'm doing something wrong. So can I solve it?
Okay. Just what you have to do. This is very simple. You have to just you have to just
multiply with
multiply
10 with 10.
10 with 2 only.
F2.
Answer will
Yeah,
be
so
20.
20 I cap plus 3 J cap plus K cap.
No, this will be removed. See how you will do. Just a minute. What you will do now? You can write this 2 I cap. You can write this 2 I cap as 2 I cap plus 0 J cap plus 0 K cap.
Yes, sir.
Now multiply coefficient of I cap with I cap, J cap with J cap, K cap and add them. So 10 into 2 is 20 plus 3 into 0 is 0 plus 1 into 0 is 0. So answer will be 20 Weaver. Okay.
Yes,
so in
sir.
this way you have to do now. Okay, just note down this question and completed, Harsh?
Second, scroll down.
Okay.
Yes, the done, sir, done.
Okay. Now try this question by yourself. This question. Okay.
Okay.
You have to apply this formula. I'm just telling you the formula. You know the formula of flux?
Yeah. Phi is equal to
B dot
BA
A
sin
or this can be written as BA.
BA sin theta. Right?
No,
So
not
yeah, cos theta. Cos
just
theta.
try this and tell me the answer. Okay, got the answer?
So just
Very easy question.
yeah, I just put the values just so that's it.
Magnetic field is given.
Area I have to find and then cost is given.
Oh, sorry. Just a minute. Actually, the area is 10 meter square given. Sorry. Actually, I have not written the area.
It's 10 meters square, sir.
Yeah, it's 10 meters square. Now you should try.
Okay.
Okay. Should I solve now?
Yes, sir, you can solve, sir. I think I'm getting wrong answer here.
Okay, no problem. See, area is given. Suppose this is the plane area. Okay, this area is 10 meter square. And they are saying the magnetic field is making an angle of 30 degree with the plane of the coil. With the plane of the coil.
Plane of the
See,
coil.
plane of the area. Okay, or plane of the area, the magnetic field is making an angle of 30 degree. So direction of the area vector will be perpendicular to the magnetic field. No, not the magnetic field. Direction of area vector will be perpendicular to the plane of the coil. Okay.
Yes, sir.
So this whole angle will be 90 degree.
Yes, sir.
Okay. So this whole angle, I am talking about this angle, this angle. This whole angle will be 90 degree. So you have to find the angle between this B and A. What will be the angle between the magnetic field and the area if this angle is 30 degree?
Cos 30, right?
No. I'm just saying.
Oh, no. B and A.
What is the angle between
If that is
B
30 and that is 90. Wait, just a minute.
Hmm.
It will be 180 minus 30.
No. Actually, see this angle, this and this angle is 90 degree. Okay, just a minute, I am writing. This whole angle is 90 degree. Okay, and this angle is 30 degree. See, this is the condition. This is the magnetic field and This is the area vector. Okay, this is and this whole angle is 90 degree and this angle is 30 degree. You have to tell this angle. Yeah, very easy.
Sir, I can't hear you, sir. Can you repeat?
I am just saying this is the magnetic field, this is the area vector. Okay, and this area vector is
Yeah.
90 degree with
Yes.
this plane of the coil.
90 degrees. So 90
So,
minus 30.
yeah, so 60 degree. 90 minus 30,
60.
60 degree.
Yeah.
Now this angle will be 60. This is very easy thing.
Uh,
Now what will be
yeah,
the
sir.
theta?
So,
Theta is
the
the,
last time I counted the whole plane.
yeah, theta is the 60 degree. What is theta here? In this formula, theta is angle between area and the magnetic
60
field.
degrees.
Now put the value VA cos theta. What is magnetic field? 2 Tesla. Area is 10. Cos of 60 degree. Do you know what is cos 60 degree? 1 by 2. Okay. So you will put the value here 2 into 10 into 1 by 2. So what will be the answer? 10 Weaver.
Yes, sir.
10 Weaver will be the answer. So actually now here you do not have to take the angle of magnetic field with the plane of the area. This is the plane of the area. You have to take the angle between the magnetic field and the area vector. So and we know that for the planar area vector is perpendicular to the plane of area. Okay, just write down.
Yes, sir. Just a minute. Done, sir.
Faraday's experiment. Next topic is Faraday's experiment.
Yes, sir.
So Faraday was the scientist. Okay, he has
So
done
just a minute,
some.
sir, just a minute. Yes, sir, you can continue, sir.
Okay, suppose this is the magnet, north pole of magnet, south pole of the magnet, and suppose this is some wire in the form of helical form, and here there is one galvanometer, or you can say this is one point A, this is another point B, this is another point C. So can you tell me at which point the magnetic field intensity due to this magnet will be less?
So magnetic
Will be
field intensity due to this magnet will be less.
will be least, not less.
It will be C,
Right?
right?
Yeah, very good, very good. Because C is far from A,
Yeah.
means farther from A and B. Okay,
Yes, sir.
this A is nearer to this magnet. So here the intensity of suppose here is magnetic field V1, here is V2, here is V3. So magnetic field intensity V1 is greater than V2 is greater than
B3.
V3. The nearer the magnet to the point and more will be the magnetic field intensity. So this concept will be used. Now see, this is the magnet, na? This is the magnet, and what will happen? What will happen when you are taking the magnet nearer to this coil? The magnetic field intensity for this coil will increase.
Yes,
Okay,
sir.
but when you will take magnet nearer to this coil, means distance between the coil and the magnet is decreasing or increasing? Decreasing.
Decreasing.
It means that magnetic field intensity due to the magnet will increase here. Okay, means you can say when this magnet is moving in this direction. This we are discussing the Faraday's experiment in my language. Okay, I am doing the experiment right now. So North Pole is this. North Pole and South Pole are there in the magnet, and this magnet is moving like this. This magnet is moving like this. So as this magnet is moving towards the coil, what will happen? The magnetic field will increase at this coil due to the motion of the magnet.
Yes, sir.
Okay, first one thing. Magnetic field increase means magnetic field will changing. Magnetic field is changing again and again as this magnet is moving from this point to this point. So magnetic field is changing at this C1 again and again. Okay, magnetic field is changing C1 again and again. So what he has observed now, when he take a magnet, he take this type of coil connected with galvanometer, then he take the magnet and somehow the he make the magnet to move towards the coil. What he has observed now, what he have observed, there will be some deflection in the galvanometer. There will be some deflection in the galvanometer, and if there is a deflection in the galvanometer, then you can say there will be the current across this coil C2.
Yes, sir.
So due to the motion of the magnet, he observed that, Faraday observed that due to the motion of the magnet, there will be some current in this coil, and that current is known as the induced current, and this is due to the induced EMF. Actually, in actual, what is the reason behind when this magnet is moving and here is some current? Because I have told you, if this magnet will move, magnetic field here will change. As the magnetic field will change, so you can say magnetic flux. Magnetic flux is equal to VA cos phi. So you can say your magnetic flux is directly proportional to magnetic field. Your magnetic field will increase, then you can say your magnetic flux will increase. So due to the change in flux, due to the change in flux here, just a minute. Sorry. Due to the change in the magnetic flux here at coil C1, there will be the some induced EMF, and due to that induced EMF, there will be the induced current. That is why there is a deflection in the galvanometer. Okay, so I am writing the reason why when the magnet is moving in this direction or away from the coil, then there will be some current here in this circuit. So motion of magnet will change Harsh, are you getting?
Yes, sir. Yes, sir.
Will change the magnetic field. Why the motion of the magnet will change the magnetic field? Means will increase the magnetic field at C1. Because distance between the magnet and the coil is increasing. That is why
Increasing.
the uh, magnetic field is increasing. So you can say magnetic motion of the magnet will change magnetic field at C1. Change means increase, you can say change or
Yes, sir.
increase. The magnetic field can decrease also when this magnet suppose moving in this direction. So distance is increasing from this
Yes,
coil.
sir.
So at the coil, the magnetic field will be less. Now the magnetic field will be more when the magnet will be nearer to this coil.
Yes, sir. Yes.
So motion of the magnet will change the magnetic field at C1, due to which magnetic flux linked with C1 changes, or you can say increase. And due to the increase or change in the magnetic flux, EMF is induced. Due to change in magnetic flux, EMF induced. Due to change in magnetic flux, EMF induced in coil, and hence there will be, due to the EMF we will get the induced current. Due to the induced EMF we will get, EMF can produce the current now. Due to the EMF
Yes, sir.
we get the current in the circuit. Okay, hence there will be induced EMF. So sorry, there will be induced current in circuit, in coil, you can say. This is the first thing. This is the first experiment done by the Faraday, and
Yes,
this is
sir.
the explanation. This is the explanation. So you should know the magnetic field is depending upon the distance, and magnetic field is also depending upon the uh, mag depending upon the current. Okay. No, sorry. Magnetic field is depending upon the distance, and magnetic flux is depending upon the magnetic field. So you can write magnetic field is depending upon the distance. R is the distance, inversely proportional to the distance. No? V is that. What is the formula for the magnetic field? Okay, no need to write down this. This is understood now?
Yes, sir. Yes.
This first experiment.
Yes, sir.
So the conclusion is that when the magnet will do the motion, there will be some current in this coil, and this is the explanation why there is the current. Now second experiment. In the second experiment, in the second experiment, Faraday took this coil, and this coil is connected with some battery. Okay, and if this coil is connected with some battery, then there will be the current flowing in this coil. Okay,
Yes,
there
sir.
will be the current flowing in this coil. So in the second experiment, this whole system is moving towards this C1.
Yes,
Towards
sir.
this C1, this whole system is moving, and there we will see there will be some deflection in the galvanometer. Now why there is some deflection? He found that there is some deflection in the galvanometer when this coil is moving in this direction, like this. So why this is happening? See, As there is some current in this coil, and due to the current in the coil, there will be the magnetic field.
Yes, sir.
There will be the magnetic field due to this coil, and there will be some due to this coil. There will be some magnetic field here also, and when this will go nearer to this C1, so magnetic field at C1 will increase or decrease.
Increase, sir.
Increase, because the distance between C1, distance between C2 and C1 is decreasing. Okay.
Yes, sir.
Okay. Now we can just say that suppose this coil is moving in this direction. This coil is moving away from the magnet. So now how we will and when this coil is moving away from the magnet, there will be some current in the galvanometer. There will be some current in this coil. So the explanation is here. A current carrying will produce the magnetic field as coil C2 moves away from this coil C2 is moving away from C1. Okay, so as the coil C2 moves away from C1, magnetic field at C1 will start decreasing. So the magnetic flux. Magnetic field at C1 is decreasing. Yes, sir. Due to that, magnetic flux will also decrease, because magnetic flux is directly proportional to the magnetic field. If magnetic field will increase, magnetic flux will increase. If magnetic field will decrease, magnetic flux will also decrease. So the magnetic flux. So due to decrease in magnetic flux, there will be some induced current. So due to this change in flux, change means this time decrease. You can change the thing by decreasing it or by increasing it. Okay. Yes, if something is changing, either it is decreasing or either it is increasing. So due to this change in flux or decrease in flux, EMF induced in C1 and induced current also. Induced current also. Third experiment. So in the third experiment, he has taken this type of system, one coil connected with galvanometer, another. So here is one, he has connected one key and he has connected one battery. When he this is the open circuit or closed circuit?
This is open, sir.
Yeah. So what will happen when he suddenly closes this key? When he suddenly closes this key, there will be some deflection in the galvanometer. Yes. So can you explain? Can you explain why this is happening? When you just close this key, there will be some deflection in the galvanometer. Do you have the explanation?
When we close the key, there is a deflection.
Somehow you have to relate this with the magnetic flux through the coil C1. See, I am explaining. Now, what is the current in C2 this time? This is open.
Yes, sir.
I am just saying, what is the current in C2 now? This time, as this switch is open, so what will be the current at C2? Current in C2?
It will be 0, right?
Yeah, suppose this is the mouse, na? This time
Yeah.
there will be some current.
Yeah.
I am just opening this circuit. Now there will be no current.
No,
Now,
sir, there won't be
now
current.
there will be current. So when you will close this key, the current will start increasing.
Yes, sir.
From 0 to maximum value.
Yes, sir.
In this coil. So what will happen? When the current will start increasing, means you can say the magnetic field due to this coil C2 at C1 will start increasing.
Yes, sir.
Because magnetic field is directly proportional to current. Magnetic field is directly proportional to current. As this I is increasing, as this
I is increasing.
I is increasing. So magnetic field at C1, magnetic field due to this at C1 will increase.
Yes, sir.
Simply. So you can say if magnetic field is increasing means the magnetic flux at C1 will increase.
Yes.
So if there will be some increase or decrease in the magnetic flux, there will be some current. So that is why there is current here and deflection of the galvanometer. So this is the explanation I have written. We will
sir.
just try to read this.
Okay.
No. I want to also listen.
Okay.
Yeah.
As soon as the key is closed, current starts increasing in coil C2, and due to which magnetic fields.
Just a minute. What you should do, na? You should just while you are reading this, na, try to imagine what is happening in the circuit. Okay.
Yeah. Okay.
Now
Yes.
read. Now read.
As soon as the key is closed, the current starts increasing in coil 2, and due to which magnetic field starts increasing, and the flux linked with C1 will become 0 to current to constant
To a
value.
constant value.
Yeah, to a constant value. So there will be current in C1 for some time, and after that there will be no current in C1. As now there will be no change in magnetic flux linked with C1.
So actually, what is happening here, na? When you suddenly closes this key, na, so suddenly suddenly for some time the current will start increasing from 0 to initially the current was 0. The current will start increasing from 0 value to some value, maximum value, and after a certain period of time the current will become 0.
Yes, sir.
Not 0, the current will become constant. When the current will become constant, magnetic field will become constant at C1. At C1 the magnetic field will become constant. When magnetic field will become constant, then you can say magnetic flux at C1 will be constant. If there is no change in the magnetic flux, then there will be no current. But suddenly there will be some current here. So as soon as the key is closed, current start increasing in coil C2, and due to which magnetic field start increasing and flux linked with the coil C1 will become 0. What I have written? Just a minute. So as soon as the key is closed, current start increasing in coil C2, due to which magnetic field.
Yeah.
Just a minute. I am just rewriting it. Due to which magnetic field starts increasing at C2 for some time.
Yes, sir.
And magnetic flux linked with C1 will increase, or you can say change. Hence, there will be some induced current. Hence, there will be some
induced current.
In C1 or C2?
C1.
Yeah, induced current in C1 for some time.
Sometime.
Here you can write, after that, when the current in C2, what will happen when you will just close this key, after certain period of time, the current in the coil C2 will become constant.
Yes,
Okay?
sir.
So after some time,
So just a minute, sir. My network is kind of lagging. So just a minute, I'll check it. Yes, sir.
okay, so after some time, what will happen after some time? The current will become constant in C2.
Yes, sir.
After some time, the current will become constant in C2, and hence no change in magnetic field, and hence
No change in magnetic field.
no change in magnetic field at C1. So no change in flux.
Yes, sir.
So no EMF induced. So no EMF. When no EMF induced, there will be no induced current. So from these experiments, what we can conclude? We can conclude that whenever uh, there will be some change in the flux with respect to the coil, then there
Yes,
will
sir.
be the induced EMF in that coil.
Yes, sir.
Okay. If flux is changing, either increasing or decreasing, then only there will be some induced current or induced EMF. Otherwise,
Yes, sir.
if there is no change in the flux linked with the coil, then there will be no induced EMF, there will be no current, no induced current. Okay. So
Yes, sir.
actually, the reason behind the study of these experiments is to know how the EMF is induced. Okay, how the
Yes, sir.
current is induced. Just copy this.
Yes, sir.
Harsh, in India, from where you belong?
Sir, Pune, Maharashtra, sir.
Pune. So, what is the language there? Hindi or
Sir, it's
something?
like mostly people in Maharashtra speak Marathi, but I speak Hindi.
Okay, Marathi. मतलब basic language there is Marathi.
Yeah, like yeah,
Okay,
there is
okay.
Marathi. But like it's like 50-50, sir. Like people speak Hindi and Marathi both of them.
You speak English, and when you came here, when you come here, or Marathi or English.
It's English, Marathi, Hindi, all of them.
You know how to speak Hindi.
Yeah, I know how to speak Hindi, sir.
In Saudi, you speak English or Arabic?
Sir, it's English only, sir.
Okay. Have you seen any Marathi movie in Marathi language?
No, sir.
Hindi movie in Hindi language?
Yes, some of those.
Okay. So, why we are studying the Faraday's experiment? Faraday has done the experiment so many years ago. Because we want to know the concept behind this magnet is moving and why there is current here.
Yes, sir.
See, this is a strange thing, na? There is no wiring. Is there is any
Yes, sir.
wiring between this
No,
magnet and
no.
this coil? There is no wiring. But then also there is a current here. This
Yes,
thing
sir.
has changed the world. This thing has changed the world. These experiment of Faraday has changed the whole world.
Okay.
You cannot imagine means how these things has changed the world. There are the generator, transformers. There are many things. There's a revolution.
So can you scroll down?
Yeah. So now just a minute. Just stop writing here.
Yes, sir. Yes, sir. Yes.
See here. This is the magnetic field.
Yeah.
Means this is a magnet, and I have told you in this chapter what we will study.
Yes, sir.
With the help of magnetic field, the current will be produced, or the current will be there. So now
Yes, sir.
see here we have the magnet, and here current is produced or current is induced. So in this chapter, this is the reverse thing. Earlier, from the current we get magnetic field. Now we are getting current from the magnetic field.
Yes, sir.
Okay, right now. So change in magnetic flux is very important thing. Very important.
Yes, sir.
Change in the magnetic flux. So whenever there will be change in the magnetic flux with respect to time, change means change of thing can be with distance, change of thing which can be anything. When there will be the change in the magnetic flux with time, then there will be some EMF induced in the coil, in the wire. We will discuss one topic, the AC generator. There also the cause of the current there will be the change in the magnetic flux.
Second, scroll down.
So on the basis of these experiments, Faraday had given a law known as Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. The theory of these experiments is important for you.
Yes, sir.
This will give you a sense of understanding what is happening, why there is some current in the coil when the magnet is moving. Actually, this is happening due to the change in the flux.
Yes,
Actually,
sir.
this is happening due to the change in the magnetic flux linked with the coil. Whenever there will be change in the magnetic flux linked with the coil, there will be some induced EMF, and this is the Faraday's law of electromagnetic induction. We will discuss that. Maybe you will not get the question from this part, but you will get the better understanding what is happening here. Means why
Yes, sir.
there will be some deflection in the galvanometer, and these things will help you in the further chapter. For the further
Yes,
chapters,
sir.
these concept will help you a lot. Done?
Yes, sir.
Okay, so after there is one law, Faraday law, and Faraday law is given on the basis of these experiments. And now we already know what is Faraday law. If there will be a change in the flux with time, then there will be the induced EMF. Okay, simple. So that we will discuss. After that, we will finish this class.
Yes, sir.
On the basis of those experiments, Faraday has given one law. See, whenever magnetic flux linked with the coil change, I have told you, an EMF induced in the coil, and this induced EMF is proportional to the rate of change of magnetic flux. Simple. And I will explain this like this. Suppose we have a magnet. Initially, we have a magnet here. Suppose time here is t1. What is time? Suppose t1 is the
T1.
time. T1 time means suppose 2 p.m. is there. 2 p.m. For example, 2 p.m.
Yes, sir.
Okay. After some time, and due to initially the magnet is here, na? Initially the magnet is here. There will be some flux linked with coil C1 due to this
Yes, sir.
magnet. Due to this magnet, there will be some magnetic field at C1. Due to the
Yes,
magnetic
sir.
field at C1, there will be some magnetic flux at C1. So there will
Yes,
be,
sir.
suppose phi1 is the magnetic flux at C1. Okay. So you can say this is the flux. Not, this is not the electric flux. Here we are talking about the magnetic flux. Flux, or you can write magnetic flux at time t1. Finally, suppose your magnet is here. As this magnet is moving, this magnet na, is moving towards the coil. So
Yes, sir.
finally, the magnet is here. Not finally, after some time, your magnet is here. You can say after some time. This is North Pole and this is South Pole. After some time, T2. After some time T2, suppose at 2.1 p.m. 2.1 p.m. means
2.1 p.m.
means 2 p.m. and 1
Yeah.
minute.
Yeah,
Means
yeah, yeah.
after 1 minute, okay? After
Yes.
1 minute. Okay, no need to write. Got it now? What I want to say?
Yes, sir. Yes,
After
sir.
2 p.m., after some time T2, after this magnet is here. Now this
Yeah.
magnet is here. Will the magnetic field due to this magnet at point C1 will increase or decrease? Increase, na? Because distance
Yeah.
is decreasing. So magnetic field
Yeah.
will, so you can say there will be some flux also. If there is some magnetic field here, due to the magnetic field, there will be some flux because flux is
Yes,
given
sir.
by the magnetic field, VA cos theta. So your flux is depending upon, magnetic flux is depending upon the magnetic field. So there will
Yes,
be
sir.
some flux phi 2, you can say flux at time T2. What is the change in the flux during this time? Delta phi.
Delta 5.
Okay. So delta phi will be the change in the flux, that is phi 2 minus phi 1.
Yes, sir.
What is change in time? That is delta t.
Delta T should be T2 minus T1.
Very good. T2 minus t1. Okay, so Faraday says that EMF induced in the coil is
Yes,
directly
sir.
proportional to change in flux
Change
with
in
respect to
flux.
change in time.
Yes, sir.
This is the Faraday law of electromagnetic induction. And when you will remove this proportionality sign, you will get a constant K, that
K.
is delta phi by delta T.
T.
K is proportionality constant, and this constant K have the value of -1 for all system of units. For
All system of units.
like we have the system of unit now, MTS system, CGS
Yes.
system,
Yes, sir.
SI system, for all
Yes, sir.
system of units. So K is equal to -1. When you will put K is equal to -1, you will get minus d phi by dt. And this d phi by dt is the Faraday law of electromagnetic induction. EMF induced is equal to minus what I have written, but this is not d phi by dt. Delta phi by delta t, na?
Yeah.
Because this is delta k. When you will put k
Yeah.
equal to 1, you will get minus delta phi by delta t.
Yes, sir.
Okay. So here you will get
Bye bye.
minus of delta phi by delta t. So this is your
Paradise.
formula, and please remember this is very important thing.
Yes, sir.
And Now, what is average EMF? Like we have the velocity, na? We have velocity.
Yes,
There
sir.
are two types of velocity: average velocity and instantaneous velocity.
Yes, sir.
Current we have written average current and instantaneous current. What is the average current? When you are just calculating current for a definite period of time.
Period of
For
time.
a for a
Definite
definite
period.
means when there is a time period, when there is some definite time period. Okay.
Yes.
Like 1 minute, 2 minutes, 3 minutes, 4 minutes. Okay, and when we want the current or when we want the EMF at time, at some time, means I am saying, tell me what is the EMF at 2 p.m. So this will be the instantaneous EMF. Means
Yes, sir.
someone is asking to you the instantaneous EMF. And if someone is saying, tell me what will be the EMF between 2 p.m. to 3 p.m. means he or she wants to know the average EMF. So average EMF is simply represented by minus delta phi by delta t.
Yes, sir.
Okay, so delta is used for instantaneous. When this will be not instantaneous, average.
Average.
For instantaneous EMF, instantaneous EMF is written by I instantaneous, and this will be what is the, when you will write here limit delta t tending to 0. Delta t tending to 0 means time interval is very small. You
Yes,
want
sir.
exactly at 2 p.m. The EMF at 2 p.m. you want. So this
Yes.
will be minus delta phi by delta
By
t.
delta t.
Yeah. And this equation can be written as minus d phi by
dt.
dt. Why I have written this equation in this form? Because delta t is tending to 0.
Yes, sir.
Delta t is tending to 0 means this dt. What is the meaning of dt? Very small time interval.
Very small time interval.
Or you can say infinitely small time interval. Very small
Yes, sir.
time interval. Time interval. What is d phi? D phi is very small, or you can
Small
say
and
infinitely small
flux.
change in flux.
Yes, infinite or change in flux.
Very okay. So no need to write. We know
Yes, sir.
what is d phi by d. So this uh, instantaneous EMF is given by the d phi by dt.
dt.
Okay, just copy this. Rest of the things we will discuss in the next. So this is
Yes,
your
sir.
heading. Write down the heading, and remember this law is very important. Okay, because this is the basics of this chapter.
Yes, sir. Done, seconds full down.
Okay.
Seconds full down.
Okay.
Done, sir.
Okay, Harsh. So I have told you there will be the Viva today of 5
Today,
to, yeah.
sir, I forgot to learn.
Okay, so